In the quiet darkness of a clear night, when you look up at the stars scattered across the velvet sky, you are witnessing just the tiniest fraction of what exists beyond our world. Each pinprick of light represents a sun, perhaps with planets of its own, worlds that may harbor life or hold secrets we cannot yet imagine. But here is the truly overwhelming truth. Even the most distant stars visible to your naked eye are practically neighbors compared to the vast expanse of space that surrounds us. Tonight, we embark on a journey through the cosmic ocean, exploring not just what we know, but the incredible vastness of what remains unknown. We will travel through regions so distant that light from them has not yet reached us, contemplate mysteries that stretch our understanding to its limits, and discover that despite all our technological achievements, we have barely begun to explore the universe we call home. Consider this: if our entire solar system were the size of a coin, the nearest star would be more than 400 kilometers away. And that star, Alpha Centauri, is just one of hundreds of billions in our galaxy alone. Beyond our Milky Way stretch, hundreds of billions of other galaxies, each containing their own countless stars and worlds. The numbers become so large they lose meaning, yet they represent real places, real destinations that exist in the darkness beyond our current reach. The universe is not just large, it is unimaginably, incomprehensibly vast. Even traveling at the speed of light, it would take over 4 years to reach our nearest stellar neighbor. To cross our own galaxy would require 100,000 years. To reach the nearest large galaxy, Andromeda, would take over 2 million years. And beyond that, galaxies stretch away into distances so great that we have special names for them, measured in billions of light years. But perhaps the most humbling realization is this: everything we have ever observed, every star catalogued, every planet discovered, every galaxy mapped, represents less than 5% of what actually exists. The rest is hidden from us, composed of mysterious dark matter and dark energy that we can detect only through their gravitational effects. We are like explorers standing on the shore of an infinite ocean, having examined only a few grains of sand. As we begin this journey together, remember that the universe is not just a place to be explored, but a source of wonder that connects us to something far greater than ourselves. In the darkness between stars, in the swirling clouds of distant nebulae, in the hearts of galaxies billions of light years away, countless mysteries wait to be discovered. The journey of exploration has only just begun, and the horizon of the unknown stretches endlessly before us. So let us venture forth into the cosmic night, knowing that every answer we find will reveal 10 new questions. Every discovery will open doors to realms we never imagined existed. The universe is vast, patient, and filled with wonders beyond our wildest dreams. And we, small as we are, carry within us the extraordinary ability to reach across the void with our minds, our instruments, and our infinite curiosity, touching the very edges of eternity itself. To truly understand how much of space remains unexplored, we must first grasp the sheer magnitude of what we are dealing with. The universe is not just big, it exists on a scale so vast that our minds struggle to comprehend it. Even the most familiar objects in our cosmic neighborhood dwarf anything we experience in our daily lives. Let us start close to home. Our planet Earth, which seems so large when we travel across its surface, is just a tiny blue marble when viewed from space. The distance from Earth to our moon is about 384,000 kilometers. To put this in perspective, you could fit 30 Earth-sized planets in the space between us and the moon. Yet this distance, which represents the farthest humans have ever traveled, is merely a whisper compared to the vastness beyond. Our sun, that brilliant star that gives us life, sits about 150 million kilometers away from Earth. Astronomers call this distance an astronomical unit, and it becomes our first stepping stone for measuring the cosmos. Light from the sun takes just over 8 minutes to reach us, traveling at the incredible speed of 300,000 kilometers per second. Nothing in the universe travels faster than light, yet even at this ultimate speed, the cosmos reveals its immense scale. The farthest planet in our solar system, Neptune, orbits at a distance of about 30 astronomical units from the Sun. This means that sunlight takes over 4 hours to reach Neptune, and the planet appears as nothing more than a faint blue dot, even through our most powerful telescopes. But Neptune is not the edge of our solar system. Far beyond it lies the Kuiper Belt, a region of icy objects and dwarf planets that extends to perhaps 50 times the Earth-Sun distance. Even further out, we encounter the Oort cloud, a vast sphere of comets and icy debris that may extend halfway to the nearest star. This cloud, which we have never directly observed, could stretch out to 100,000 astronomical units from the Sun. It represents the true edge of our solar system, a boundary so distant that it takes light over a year to cross it. Now we begin to use a new unit of measurement, the light year. 1 light year is the distance light travels in a full year, about 9.5 trillion kilometers. The nearest star to our Sun, Alpha Centauri, lies just over 4 light years away. To reach it with our fastest spacecraft would take tens of thousands of years. The space between stars is so empty, so vast, that if our Sun were the size of a marble, Alpha Centauri would be another marble 2,000 kilometers away. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. These stars are arranged in a great spiral disk with spiral arms reaching out from a central bulge. The galaxy spans about 100,000 light years from edge to edge, and we sit roughly 26,000 light years from the center. When we look toward the center of our galaxy on a clear night, we see that bright band of stars stretching across the sky, but we are seeing only a tiny fraction of the stars that actually exist there. The space between galaxies dwarfs even the space between stars. Our nearest large galactic neighbor, the Andromeda Galaxy, lies about 2.5 million light-years away. Between us and Andromeda stretches an almost perfect vacuum, with perhaps a few atoms per cubic meter. This intergalactic space is so empty that a person could travel through it for billions of years without encountering a single particle of matter. But galaxies are not scattered randomly through space. They cluster together in groups and superclusters, connected by vast filaments of dark matter. Our own galaxy is part of what astronomers call the local group, which includes Andromeda, the Triangulum Galaxy, and several dozen smaller galaxies. This local group is itself part of the Virgo supercluster, which contains thousands of galaxies spread across 110 million light-years. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends about 46 billion light-years in every direction. This might seem contradictory, since the universe is only about 13.8 billion years old, but space itself has been expanding during the time light has been traveling toward us. The most distant galaxies we can see appear as they were when the universe was very young, their light having traveled across expanding space for billions of years to reach us. Yet even this observable universe, vast as it is, may represent only a tiny fraction of the total universe. Many cosmologists believe that the universe extends far beyond what we can observe, perhaps infinitely. There may be regions of space so distant that their light will never reach us, no matter how long we wait. These regions exist, but they are forever beyond our ability to study or explore. As we contemplate these distances, we begin to understand the true challenge of space exploration. We have sent robotic probes to the outer planets of our solar system, a journey that takes years or decades. We have detected planets around other stars, but we have no way to visit them with current technology. We have observed galaxies billions of light years away, but they might as well be in another universe for all the possibility we have of reaching them. The universe reveals itself to us in layers of distance and time. The further we look, the deeper into the past we see. The most distant galaxies appear as they were when the universe was young, their light having traveled across expanding space for over 13 billion years. We are archaeologists of space, studying the cosmos not as it is, but as it was at different epochs of history. So when we ask how much of space remains unexplored, we must recognize that we are not just dealing with distant places, but with a cosmos so vast that most of it lies forever beyond our reach. Even the nearest stars represent journeys that would take thousands of human lifetimes with our current technology. The galaxies we see through our telescopes are like distant islands in an ocean of space, beautiful to observe but impossible to visit. In this cosmic ocean, we are like swimmers who have barely gotten their feet wet. We have explored our immediate neighborhood, sent probes to nearby shores, and gazed with wonder at distant horizons. But the vast majority of the universe remains as mysterious and unreachable as it was when humans first looked up at the stars and wondered what lay beyond the darkness. The methods we use to measure these vast distances are themselves marvels of human ingenuity. For nearby stars, astronomers use parallax, watching how a star appears to shift position as Earth orbits the Sun. It is like closing one eye, then the other, and watching how a distant object seems to move against the background. But this method only works for stars within a few hundred light years of us. Beyond that, the shifts become too small to measure accurately. For more distant objects, we rely on standard candles, objects whose brightness we understand. Certain types of variable stars pulse with predictable patterns, and by comparing how bright they appear to how bright they should be, we can calculate their distance. Type 1. A supernovae, exploding stars that reach nearly the same peak brightness, serve as lighthouses across billions of light years of space. The redshift of distant galaxies tells us about the expansion of the universe itself. As space expands, it stretches the wavelengths of light, shifting them toward the red end of the spectrum. The more distant a galaxy, the faster it appears to be moving away from us, and the more its light is red-shifted. This cosmic expansion means that the universe is not only vast, but growing larger every moment. When we observe the cosmic microwave background, we are seeing the universe as it was just 380,000 years after the Big Bang. This ancient light has been traveling through space for over 13 billion years, and it fills the entire observable universe with a faint glow. It is the oldest light we can see, a fossil remnant of the early universe when it first became transparent to light. The cosmic web, that vast network of matter that connects galaxies across the universe, reveals structure on the largest scales imaginable. Galaxies are not randomly distributed, but follow threads of dark matter that span hundreds of millions of light years. Between these threads lie cosmic voids, vast empty regions where few galaxies exist. These voids are so large that if our galaxy were placed in the center of one, we would see almost no other galaxies in any direction. Dark matter, which makes up about 27% of the universe, remains completely invisible to us. We can detect its presence only through its gravitational effects on visible matter and light. It outweighs ordinary matter by more than 5 to 1, yet we have no idea what it is made of. Entire galaxies and galaxy clusters are held together by dark matter halos that we cannot see directly. Even more mysterious is dark energy, which makes up about 68% of the universe. This strange force is causing the expansion of the universe to accelerate, pushing galaxies apart at an ever-increasing rate. We discovered dark energy only in 1998, and we still have no idea what it is or how it works. It permeates all of space yet remains completely undetectable except through its effects on cosmic expansion. The multiverse theory suggests that our observable universe might be just one of countless others, each with its own physical laws and properties. If true, then the question of how much space remains unexplored becomes even more staggering. We might be dealing not just with one vast universe, but with an infinite number of them, each containing its own galaxies, stars, and planets. As we push the boundaries of observation with ever more powerful telescopes, we continue to discover that the universe is stranger and more complex than we ever imagined. The James Webb Space Telescope is showing us galaxies that formed when the universe was very young, challenging our understanding of how quickly structures could form after the Big Bang. Each new discovery reveals new mysteries, new questions that push the frontier of the unknown even further into the distance. The speed of light, which seemed so fast when we first measured it, now appears frustratingly slow when we consider cosmic distances. Even traveling at light speed, we could not explore our own galaxy in a human lifetime. To reach the nearest star would take over 4 years, and to travel to the center of our galaxy would take 26,000 years. The universe sets fundamental limits on exploration that no technology can overcome. Yet perhaps the most profound realization is that we are part of this vast cosmos, made of the same elements that were forged in the hearts of ancient stars. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were created in stellar furnaces billions of years ago. We are not separate from the universe, but intimately connected to it, cosmic beings contemplating our own cosmic home. In the end, the scale of the universe serves as both humbling reminder and inspiring challenge. It shows us how small we are in the cosmic scheme, yet also how remarkable it is that we can understand and measure these vast distances at all. Every photon of light that reaches our telescopes is a messenger from the depths of space and time, carrying information about worlds and events far beyond our ability to visit, but not beyond our ability to comprehend. While the vast universe beyond our solar system captures our imagination, it is remarkable how much mystery remains right here in our own cosmic neighborhood. Even after centuries of observation and decades of space exploration, our solar system continues to harbor secrets, hidden worlds, and unexplored regions that challenge our understanding of planetary formation and the possibility of life beyond Earth. The outer reaches of our solar system represent one of the last great frontiers within our cosmic backyard. Beyond the orbit of Neptune lies a realm that until recently was almost completely unknown to us. The Kuiper Belt, a vast ring of icy objects and dwarf planets, extends from about 30 astronomical units from the Sun to perhaps 50 astronomical units. This region contains thousands of objects larger than 100 kilometers across and millions of smaller ones, yet we have directly visited only a handful of them. Pluto, once considered our 9th planet and now classified as a dwarf planet, reigns as the most famous resident of the Kuiper Belt. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a world of stunning complexity. Far from the dead, frozen ball of ice that scientists expected, Pluto showed active geology, possible subsurface oceans, and a complex atmosphere. Its largest moon, Charon, proved equally fascinating, with vast canyons and mysterious dark regions that scientists are still trying to understand. The flight of New Horizons through the Kuiper Belt represents humanity's first detailed look at this distant realm. After passing Pluto, the spacecraft continued on to encounter Arrokoth, formerly known as 2014 MU69, a strange double-lobed object that provided our first close-up view of a pristine remnant from the early solar system. These encounters revealed that the Kuiper Belt is not a uniform collection of similar objects, but a diverse region filled with worlds that each tell their own story of cosmic evolution. Yet for every object we have studied up close, thousands more remain mysterious points of light in our telescopes. The dwarf planets Makemake, Haumea, and Eris orbit in the outer darkness, their surfaces and compositions largely unknown. Each of these worlds is likely unique, with its own geology, atmosphere, and history. Some may harbour subsurface oceans, others may have active geology driven by tidal forces or radioactive decay. We simply do not know, and with current technology, detailed exploration of these distant worlds remains a dream for future generations. Beyond the Kuiper Belt lies the scattered disk, a region of objects with highly elongated orbits that may extend to 100 astronomical units from the Sun. These objects, including the dwarf planet Sedna with its extreme orbit, hint at a violent past when gravitational interactions with passing stars or rogue planets may have scattered objects to these distant reaches. The scattered disk represents our solar system's most remote permanent residence, worlds so distant that the Sun appears as nothing more than a bright star in their skies. But even the scattered disk may not represent the true edge of our solar system. Far beyond, in the cold darkness between 1,000 and 100,000 astronomical units from the Sun, lies the hypothetical Oort cloud. This vast sphere of comets and icy debris has never been directly observed, yet we infer its existence from the long-period comets that occasionally fall toward the Sun from random directions. The Oort cloud may contain trillions of objects, a vast reservoir of primitive material left over from the formation of the solar system. The search for Planet 9, a hypothetical large planet that may orbit in the outer solar system, represents one of the most intriguing mysteries in modern astronomy. The unusual clustering of orbits among certain Kuiper Belt objects suggests the gravitational influence of an unseen world, perhaps 5 to 10 times more massive than Earth, orbiting between 200 and 1,000 astronomical units from the Sun. If Planet 9 exists, it would be a dark, cold world, where the Sun provides less heat than a full moon on Earth. Yet it would be the 5th largest planet in our solar system. Closer to home, the moons of the outer planets harbour some of the most intriguing possibilities for life beyond Earth. Europa, one of Jupiter's 4 largest moons, hides a vast ocean beneath its icy crust. This ocean may contain twice as much water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's immense gravitational pull. The ocean lies beneath 15 to 25 kilometers of ice, completely hidden from direct observation, yet it may be one of the most promising places to search for extraterrestrial life. The surface of Europa shows clear evidence of recent geological activity, with vast cracks, ridges, and areas where the ice appears to have been renewed. Some regions show signs of material from the subsurface ocean breaking through to the surface, creating the possibility that future missions might sample ocean material without having to drill through the ice. The composition of Europa's ocean remains largely unknown, but it likely contains dissolved salts and possibly organic compounds that could support life. Enceladus, a small moon of Saturn, has surprised scientists with its active geology and subsurface ocean. The Cassini spacecraft detected water vapor and ice particles erupting from the moon's south pole, creating a vast plume that extends hundreds of kilometers into space. These eruptions provide a window into the moon's interior, revealing that beneath the ice lies a global ocean in direct contact with the rocky core. This contact between water and rock could create the chemical conditions necessary for life. The plumes of Enceladus contain not just water ice, but also organic compounds, salts, and possibly hydrocarbons. The moon's small size means it should have frozen solid long ago, yet tidal heating from Saturn keeps its ocean liquid and drives the geological activity that creates the plumes. Future missions might be able to sample these plumes directly. analyzing their composition for signs of biological activity without ever landing on the moon's surface. Titan, Saturn's largest moon, presents a world unlike anywhere else in the solar system. Its thick atmosphere and surface lakes of liquid methane and ethane create an environment that some scientists compare to early Earth. Titan's atmosphere is primarily nitrogen, like Earth's, but it also contains methane and complex organic molecules created by the interaction of sunlight with atmospheric gases. This organic chemistry, combined with the presence of liquid on the surface, makes Titan a fascinating laboratory for studying the kinds of processes that might lead to life. Beneath Titan's surface, scientists believe there may be another ocean, this one composed of liquid water mixed with ammonia. This subsurface ocean would be yet another potential habitat for life, adding to the growing list of ocean worlds in our solar system. The Dragonfly mission, scheduled to launch in the 2020s, will send a nuclear-powered helicopter to explore Titan's surface, studying its organic chemistry and searching for signs of past or present life. The exploration of these distant moons represents one of the greatest challenges in solar system science. The journey to Jupiter or Saturn takes years, and the harsh radiation environment around these giant planets makes long-term missions extremely difficult. The ice covering the subsurface oceans of Europa and Enceladus may be dozens of kilometers thick, requiring advanced drilling technology to reach the liquid water beneath. Yet the potential rewards are enormous, as these moons may harbor the first extraterrestrial life forms ever discovered. Mars, though much closer and more thoroughly explored, still holds vast unexplored regions and unanswered questions. The planet's polar ice caps contain layers of ice and dust that preserve a record of Martian climate history, yet we have barely begun to study these archives. The deep subsurface of Mars remains largely unknown and may contain liquid water, organic compounds, or even microbial life surviving in the planet's interior. The asteroid belt, that vast collection of rocky debris between Mars and Jupiter, contains hundreds of thousands of objects, yet we have visited only a few dozen. Each asteroid is a unique world with its own composition, structure, and history. Some asteroids may be fragments of ancient planets that were destroyed during the solar system's violent youth, while others may be pristine remnants of the original building blocks from which planets formed. The diversity of asteroid compositions suggests that the early solar system was a much more complex and dynamic place than we once imagined. Recent discoveries have revealed that our solar system extends far beyond what we once thought possible. The detection of interstellar objects like Oumuamua and 2I Borisov, visitors from other star systems passing through our solar system, suggests that space between stars may be filled with rogue planets, asteroids, and comets ejected from their home systems. These interstellar travelers provide a glimpse of planetary systems around other stars, yet they pass through our neighborhood so quickly that we have little time to study them. The search for life within our solar system has expanded beyond the traditional habitable zone around the Sun. The discovery of subsurface oceans on multiple moons suggests that life might exist in environments completely different from Earth's surface. These ocean worlds, heated by tidal forces rather than stellar radiation, could represent the most common type of habitable environment in the galaxy. If life exists in these hidden oceans, it would fundamentally change our understanding of where and how life can arise. The technology required to explore these distant worlds pushes the boundaries of human engineering. The extreme cold of the outer solar system, where temperatures drop to -200 degrees Celsius or lower, creates challenges for spacecraft electronics and mechanical systems. Solar panels become useless at such distances from the Sun, requiring missions to rely on nuclear power sources that can operate for decades in the harsh environment of space. Communication delays add another layer of complexity to outer solar system exploration. Radio signals from a spacecraft near Pluto take over 4 hours to reach Earth, making real-time control impossible. Every command must be planned carefully, and spacecraft must be designed to operate autonomously for long periods. When problems arise, mission controllers must wait hours to learn what happened, and hours more for their solutions to reach the spacecraft. The vast distances involved mean that launch windows to the outer planets occur only once every few years or decades. The alignment of planets that allowed the Voyager spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in a single mission happens only once every 176 years. Missing a launch window can delay a mission by years, and the long travel times mean that scientists who design these missions may retire before their spacecraft reach their destinations. The moons of Uranus and Neptune remain almost completely unexplored, known to us only through the brief encounters of Voyager 2 in the 1980s. Miranda, one of Uranus's moons, showed evidence of extraordinary geological activity, with vast canyons and cliffs that suggest a complex geological history. Triton, Neptune's largest moon, appears to have active geysers of nitrogen erupting from its surface. Yet we know almost nothing about what drives this activity or what lies beneath the moon's surface. The ice giant planets themselves, Uranus and Neptune, remain poorly understood despite being the third and fourth largest planets in our solar system. Their unusual magnetic fields, extreme weather patterns, and interior structures differ significantly from the gas giants Jupiter and Saturn. Uranus rotates on its side, possibly the result of a collision with a large object early in its history, while Neptune's winds reach speeds of over 2,000 kilometers per hour, the fastest in the solar system. The small moons and ring systems of the outer planets harbor their own mysteries. Saturn's moon, Iapetus, has a strange ridge that runs around its equator, giving it a walnut-like appearance, while its surface shows a stark contrast between dark and light regions. The origin of these features remains unknown, and theories range from ancient impact events to exotic processes involving the collapse of a temporary ring system around the moon. Pan and Daphnis, small moons that orbit within Saturn's rings, create gaps and waves in the ring material through their gravitational influence. These shepherd moons demonstrate the complex dynamics of ring systems, yet we understand very little about how they formed or evolved. The rings themselves may be much younger than the planets they orbit, possibly formed from the breakup of moons or captured comets within the last few 100 million years. The Trojan asteroids, which share Jupiter's orbit but remain 60 degrees ahead of or behind the planet, represent another largely unexplored population of objects. These asteroids may be remnants from the early solar system, preserved in gravitational safe havens for billions of years. The Lucy mission, launched in 2021, will visit several Trojan asteroids, providing our first close-up look at these ancient objects, centaurs, objects that orbit between Jupiter and Neptune, may be transitional objects between the Kuiper Belt and the inner solar system. Some centaurs show comet-like activity despite their distance from the Sun, suggesting complex surface chemistry or subsurface ice deposits. Chiron, the largest known centaur, has rings around it, making it one of the smallest objects in the solar system known to have a ring system. The irregular moons of the outer planets, which orbit in retrograde or highly inclined orbits, are likely captured asteroids or Kuiper Belt objects. These moons preserve information about the early solar system and the processes that shaped the outer planets. Many of these moons remain unnamed points of light in our telescopes, their compositions, structures, and histories completely unknown. Recent discoveries have revealed that our solar system is far more active and dynamic than previously thought. The detection of active volcanism on Io, geysers on Enceladus, and possible cryovolcanism on Europa shows that many worlds remain geologically active billions of years after their formation. This activity suggests that the conditions for life may persist in hidden environments throughout the solar system. The study of meteorites provides clues about the composition and history of asteroids and other small bodies, but these samples represent only a tiny fraction of the diversity that exists. Most meteorites come from just a few asteroid families, leaving vast populations of objects unsampled. The recent sample return missions to asteroids Bennu and Ryugu have provided pristine samples from specific asteroids, but thousands of other asteroids await similar detailed study. The search for potentially hazardous asteroids has revealed that our solar system contains many more large asteroids than previously thought. The discovery of objects like 2002 AA29, which passed closer to Earth than the Moon, shows that we are still cataloguing the population of objects that could pose a threat to our planet. Understanding these objects requires not just detecting them, but studying their compositions, structures, and orbits in detail. The outer solar system may harbour many more dwarf planets waiting to be discovered. The recently discovered objects Farot and Farfarout orbit at distances greater than 100 astronomical units from the Sun, in regions where surveys have barely begun. These extreme objects may provide clues about the formation and evolution of the outer solar system, as well as the possible existence of Planet 9. The heliosphere, the bubble of solar wind that surrounds our solar system, extends far beyond the orbit of Pluto. The Voyager spacecraft crossed the boundary of the heliosphere, called the heliopause, providing our first direct measurements of interstellar space. But the shape and dynamics of the heliosphere remain poorly understood, and its interaction with the interstellar medium may influence the climate and habitability of planets throughout the solar system. As we stand on the threshold of a new era of solar system exploration, with missions planned to Europa, Titan, and other ocean worlds, we are reminded that our cosmic neighborhood still holds countless secrets. Each new discovery reveals unexpected complexity and raises new questions about the processes that shaped our solar system and the potential for life beyond Earth. The journey of exploration within our own solar system has only just begun, and the most exciting discoveries may still lie ahead. In the vast tapestry of the cosmos, there exists a profound mystery that challenges our understanding of reality itself. The universe we see, with all its brilliant stars, glowing galaxies, and swirling nebulae, represents only a small fraction of what actually exists. The rest of the cosmos is composed of substances so mysterious that we can detect them only through their gravitational effects, invisible forces that shape the very structure of space and time, yet remain completely hidden from our direct observation. This hidden universe begins with dark matter, a substance that makes up approximately 27% of all matter and energy in the cosmos. Despite being 5 times more abundant than ordinary matter, dark matter has never been directly detected by any instrument on Earth or in space. We know it exists because of its gravitational influence on visible matter, bending the paths of light, holding galaxies together, and creating the cosmic web that gives structure to the universe on the largest scales. The first hints of dark matter came in the 1930s, when astronomer Fritz Zwicky studied the motion of galaxies in the Coma cluster. He found that the galaxies were moving so fast that the cluster should have torn itself apart long ago, unless there was much more matter present than what could be seen. Zwicky called this missing matter dark matter, and his observations marked the beginning of one of the greatest mysteries in modern science. When astronomers Vera Rubin and Kent Ford studied the rotation curves of spiral galaxies in the 1970s, they made a discovery that would revolutionize our understanding of the universe. They found that stars in the outer regions of galaxies were moving much faster than expected based on the amount of visible matter. According to Newton's laws of gravitation, these outer stars should have been moving more slowly, or they should have been flung out of their galaxies entirely. The solution to this puzzle required the existence of vast halos of dark matter surrounding every galaxy. These halos extend far beyond the visible stars and contain several times more mass than all the ordinary matter in the galaxy combined. The dark matter creates a gravitational well that holds the galaxy together, allowing the outer stars to maintain their high orbital speeds without escaping into intergalactic space. Computer simulations of cosmic evolution show that dark matter played a crucial role in forming the large-scale structure of the universe. In the early cosmos, tiny fluctuations in the density of dark matter grew over time, eventually becoming the scaffolding upon which galaxies and galaxy clusters formed. Without dark matter, the universe would be a very different place, perhaps one where galaxies never formed at all and stars remained scattered throughout empty space. The nature of dark matter remains one of the most pressing questions in physics. Scientists have proposed numerous candidates for what dark matter might be, from exotic particles called WIMPs, or weakly interacting massive particles, to axions, sterile neutrinos, and even primordial black holes formed in the early universe. Despite decades of searching with increasingly sensitive detectors, dark matter particles have not been directly observed, leading some scientists to question whether dark matter exists at all, or whether our understanding of gravity needs to be modified. Underground laboratories around the world house detectors designed to catch dark matter particles as they pass through the Earth. These experiments look for the tiny flashes of light or heat that might be produced when a dark matter particle collides with an atomic nucleus. The detectors are shielded by kilometers of rock to block cosmic rays and other sources of interference, yet they have found no conclusive evidence of dark matter interactions. The Large Hadron Collider at CERN has also searched for dark matter by trying to create dark matter particles in high-energy collisions. The idea is that if dark matter particles exist, they might be produced when protons are smashed together at tremendous energies. These particles would then escape the detector, leaving behind a signature of missing energy. Despite years of searching, no clear evidence of dark matter production has been found. Even more mysterious than dark matter is dark energy, which makes up approximately 68% of the universe. Dark energy was discovered only in 1998, when two teams of astronomers studying distant supernova made a shocking discovery. They expected to find that the expansion of the universe was slowing down due to the gravitational attraction of matter, but instead they found that the expansion was accelerating. This acceleration implies the existence of a repulsive force that pushes space itself apart, working against the attractive force of gravity. Astronomers called this mysterious force dark energy, and its discovery fundamentally changed our understanding of the universe's fate. Instead of eventually collapsing back in on itself or coasting to a halt, the universe appears destined to expand forever, with galaxies moving apart at an ever-increasing rate. The nature of dark energy is even more mysterious than dark matter. One possibility is that dark energy is simply the energy of empty space itself, a quantum mechanical property called vacuum energy. According to quantum field theory, even empty space is filled with virtual particles that pop into existence and disappear on timescales so short that they cannot be directly observed. The energy associated with these quantum fluctuations could be what we observe as dark energy. However, when physicists calculate the expected amount of vacuum energy, they get a result that is larger than the observed dark energy by a factor of 10 to the power of 120. This discrepancy is so enormous that it represents one of the worst predictions in the history of physics. Clearly, our understanding of either quantum mechanics or general relativity, or both, must be incomplete. Another possibility is that dark energy is a dynamic field, similar to the field that drove cosmic inflation in the early universe. This field, sometimes called quintessence, could vary in strength over time and space, leading to a more complex evolution of cosmic acceleration than what is predicted by a simple cosmological constant. Observations of distant supernovae and other cosmological probes are beginning to test whether dark energy is truly constant or whether it changes over time. The cosmic microwave background, that ancient light from the early universe, provides another window into the dark universe. Tiny fluctuations in the temperature of this background radiation reveal the distribution of matter and energy when the universe was only 380,000 years old. These fluctuations show the fingerprints of dark matter and dark energy, providing precise measurements of their abundance and properties. The Planck satellite, which mapped the cosmic microwave background with unprecedented precision, confirmed that the universe is composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. These measurements are so precise that they have established a standard model of cosmology, yet they also highlight how little we understand about the dominant components of the universe. Gravitational lensing provides another tool for studying dark matter. When light from a distant galaxy passes through a cluster of galaxies, the gravitational field of the cluster bends the light, creating distorted images or multiple images of the background galaxy. By studying these lensing effects, astronomers can map the distribution of dark matter in galaxy clusters, revealing structures that are completely invisible to ordinary telescopes. Some of the most dramatic examples of gravitational lensing occur when dark matter acts as a cosmic magnifying glass, brightening and distorting the images of galaxies billions of light years away. These natural telescopes allow astronomers to study the early universe in greater detail than would otherwise be possible, revealing galaxies that formed when the universe was less than 1 billion years old. The collision of galaxy clusters provides a natural laboratory for studying dark matter. When two clusters collide, the ordinary matter, which consists mostly of hot gas, interacts and slows down due to electromagnetic forces. Dark matter, however, interacts only through gravity and passes right through the collision with little effect. This separation of dark matter from ordinary matter has been observed in several cluster collisions, providing strong evidence that dark matter truly exists as a separate component of the universe. The Bullet Cluster, located about 3.8 billion light-years from Earth, represents one of the most convincing pieces of evidence for dark matter. In this system, two galaxy clusters have collided and passed through each other, leaving the hot gas behind while the dark matter and galaxies continued onward. Gravitational lensing maps show that most of the mass in the system is located with the galaxies, not with the hot gas, exactly as predicted if dark matter exists. The cosmic web, that vast network of dark matter filaments that connects galaxies across billions of light years, represents the largest structures in the universe. Computer simulations show that dark matter forms a web-like pattern, with dense nodes where galaxy clusters form and thin filaments connecting them. The galaxies we see are like lights strung along this invisible scaffolding, revealing only a small fraction of the underlying structure. Recent observations have begun to detect the cosmic web directly by observing the faint emission from hydrogen gas that lies along the dark matter filaments. This intergalactic medium is so tenuous that it produces only the faintest glow, yet it traces the cosmic web on scales of hundreds of millions of light years. These observations provide the first direct view of the largest structures in the universe. The regions between the filaments of the cosmic web are called cosmic voids, vast empty spaces that contain very few galaxies. These voids can be hundreds of millions of light years across, so large that if our galaxy were placed in the center of one, we would see almost no other galaxies in any direction. The voids make up about 80% of the universe's volume, yet they contain only a small fraction of its matter. The properties of cosmic voids provide important clues about dark energy. Because voids contain very little matter, they are dominated by dark energy, which causes them to expand faster than average. Studying the size and evolution of voids can help astronomers understand how dark energy has influenced the growth of cosmic structure over billions of years. Future surveys will map billions of galaxies and measure their positions and distances with unprecedented precision. These maps will reveal the cosmic web in exquisite detail and provide new tests of our understanding of dark matter and dark energy. Projects like the Vera Rubin Observatory will observe billions of galaxies, creating the most detailed map of cosmic structure ever assembled. As we probe deeper into the dark universe, we are confronted with the humbling realization that most of the cosmos is composed of substances that we do not understand. The ordinary matter that makes up stars, planets, and life represents only a tiny fraction of the universe, while the dominant components remain mysterious. We are like explorers in a vast, dark ocean, able to see only the occasional island of light, while the depths remain hidden from view. The search for dark matter and the quest to understand dark energy represents some of the greatest challenges in modern science. They push us to develop new theories of physics, build more sensitive detectors, and explore the universe with ever more powerful telescopes. Each new observation brings us closer to understanding the true nature of the cosmos, yet also reveals how much more there is to discover in the dark side of the universe. In the quiet hours of a clear night, as we gaze up at the countless stars scattered across the cosmic dome, one question echoes through the chambers of human consciousness more persistently than any other. Are we alone? In this vast universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, does life exist elsewhere? Or are we truly the only conscious beings contemplating our place in the cosmos? The search for extraterrestrial life represents one of humanity's most profound scientific endeavors, touching the very core of what it means to be alive and aware in an apparently infinite universe. Yet despite decades of searching, with increasingly sophisticated instruments and methods, we have found no definitive evidence of life beyond Earth. This absence of discovery raises as many questions as it answers, leading us to wonder not just where life might exist, but why we have not yet found it. The modern search for extraterrestrial life began in earnest with the discovery of exoplanets, worlds orbiting stars other than our Sun. The first confirmed exoplanet around a Sun-like star, 51 Eridani b, was discovered in 1995, opening a new chapter in astronomy and astrobiology. Since then, space telescopes like Kepler, TESS, and ground-based surveys have discovered over 5,000 confirmed exoplanets, with thousands more awaiting confirmation. These discoveries have revealed that planets are extraordinarily common throughout the galaxy. Nearly every star appears to host at least one planet, and many stars have multiple worlds orbiting them. The diversity of exoplanets is staggering, ranging from super-Earths with masses several times that of our planet, to hot Jupiters that orbit closer to their stars than Mercury orbits our Sun, to frozen worlds in the outer reaches of their stellar systems. The concept of the habitable zone, sometimes called the Goldilocks zone, defines the region around a star where liquid water could exist on a planet's surface. This zone is neither too hot nor too cold, but just right for water to remain in its liquid state. For our Sun, the habitable zone extends roughly from the orbit of Venus to the orbit of Mars, with Earth sitting comfortably in the middle of this zone. Kepler 452b, discovered in 2015, was hailed as one of the most Earth-like planets ever found. Orbiting a Sun-like star in the constellation Cygnus, this world receives about 10% more energy from its star than Earth receives from the Sun. The planet is about 60% larger than Earth and orbits its star every 385 days, remarkably similar to Earth's year. Yet despite its promising characteristics, Kepler 452b lies about 1,400 light-years away, making it impossible to study in detail with current technology. The TRAPPIST-1 system, located 39 light-years from Earth, contains 7 Earth-sized planets, 3 of which orbit in the habitable zone of their red dwarf star. This remarkable system offers the best opportunity for detailed study of potentially habitable worlds, as the planets regularly pass in front of their star as seen from Earth, allowing astronomers to analyze their atmospheres using spectroscopy. Future space telescopes may be able to detect water vapor, oxygen, or even biosignatures in the atmospheres of these worlds. The James Webb Space Telescope has begun analyzing the atmospheres of exoplanets with unprecedented precision, searching for the chemical signatures that might indicate the presence of life. Water vapor, carbon dioxide, methane, and oxygen all leave distinct fingerprints in starlight as it passes through a planet's atmosphere. The detection of certain combinations of gases, particularly oxygen and methane together, could indicate biological processes at work. Yet the search for atmospheric biosignatures faces significant challenges. Many gases that could indicate life can also be produced by non-biological processes. Oxygen, for example, can be created by the breakdown of water molecules in a planet's upper atmosphere, while methane can be produced by volcanic activity or chemical reactions in the planet's interior. Distinguishing between biological and non-biological sources of these gases requires careful analysis and multiple observations. The Fermi paradox, named after physicist Enrico Fermi, poses one of the most troubling questions in the search for extraterrestrial life. Given the vast number of stars in the galaxy, the age of the universe, and the apparent commonality of planets, why have we not detected any signs of intelligent life? If civilizations are common, some should be millions or billions of years older than humanity, with technology far beyond our current capabilities. Various solutions to the Fermi paradox have been proposed, each with profound implications for our understanding of life and intelligence in the universe. The Great Filter hypothesis suggests that there is some step in the evolution of life that is extremely difficult to pass, preventing most life from reaching intelligence or technological capability. This filter could be the origin of life itself, the development of complex cells, the evolution of intelligence, or the ability to survive technological advancement. Another possibility is that intelligent civilizations do exist, but choose to remain hidden from detection. Perhaps advanced civilizations recognize the dangers of revealing their presence to potentially hostile neighbors, leading to a cosmic conspiracy of silence. Or perhaps they exist in forms so different from our own that we cannot recognize them as intelligent life, communicating through methods we have not yet imagined. The concept of cosmic intelligence may be fundamentally different from human intelligence. While we search for radio signals and other technological signatures, alien intelligence might operate on completely different principles. Machine intelligence, uploaded consciousness, or even quantum computational systems could represent forms of intelligence that bear no resemblance to biological life as we understand it. The search for extraterrestrial intelligence, known as SETI, has been listening for artificial radio signals from space for over 60 years. The project began with astronomer Frank Drake's observations at Green Bank Observatory in 1960 and has since expanded to include radio telescopes around the world. SETI searches focus on frequencies where natural cosmic noise is minimal, reasoning that intelligent civilizations would choose these quiet channels for communication. The famous WOW signal, detected in 1977 by the Big Ear radio telescope, remains one of the most intriguing candidates for an artificial extraterrestrial signal. The signal lasted 72 seconds and appeared to come from the direction of the constellation Sagittarius, but it was never detected again despite numerous follow-up observations. The signal's characteristics matched what scientists expected from an artificial transmission, yet its one-time appearance leaves its origin uncertain. Modern SETI efforts use sophisticated algorithms to search through vast amounts of radio data, looking for patterns that might indicate intelligence. The Allen Telescope Array in California can monitor millions of stars simultaneously, while the Breakthrough Listen project uses some of the world's largest radio telescopes to conduct the most comprehensive search for extraterrestrial intelligence ever undertaken. The search for technosignatures, evidence of technology in space, has expanded beyond radio signals to include other potential indicators of advanced civilizations. Dyson spheres, hypothetical megastructures built around stars to capture their energy, would create distinctive patterns in starlight that might be detectable with space telescopes. The dimming patterns of stars like Tabby's star have sparked speculation about possible artificial structures, though natural explanations remain more likely. Optical SETI searches for brief flashes of laser light that might be used for interstellar communication. Advanced civilizations might use powerful lasers to send signals across space, creating brief but intense pulses of light that could be detected by sensitive instruments. These searches require precise timing and coordination, as laser pulses would last only microseconds and might be aimed at Earth for only brief periods. The possibility of ancient alien artifacts in our solar system has captured the imagination of scientists and the public alike. If extraterrestrial civilizations visited our solar system millions or billions of years ago, they might have left behind evidence of their presence. The search for extraterrestrial artifacts, or SETA, involves looking for unusual objects or structures that might be of artificial origin. The asteroid Oumuamua, which passed through our solar system in 2017, sparked intense debate about its origin and nature. Its unusual elongated shape, lack of visible comet activity, and slight acceleration as it moved away from the Sun led some scientists to speculate that it might be an artificial object. While most astronomers believe Oumuamua is a natural asteroid or comet from another star system, its strange properties remind us how little we know about objects from interstellar space. The moons of the outer planets in our solar system offer some of the most promising locations to search for life. Europa's subsurface ocean, Enceladus's water plumes, and Titan's complex organic chemistry create environments where life might exist in forms very different from Earth life. These locations require different search strategies, focusing on chemical biosignatures rather than technological signals. The concept of a shadow biosphere suggests that life on Earth itself might be more diverse than we realize. If life arose independently multiple times on our planet, or if early life evolved along different biochemical pathways, there might be forms of life existing alongside us that we have not yet recognized. These organisms might use different genetic codes, metabolic pathways, or even different fundamental chemistry, making them invisible to conventional biological surveys. Extremophiles, organisms that thrive in conditions once thought impossible for life, have expanded our understanding of where life might exist. From the superheated waters of deep-sea volcanic vents to the highly acidic pools of Yellowstone, from the radiation-soaked walls of nuclear reactors to the salt-crusted deserts of Chile, life has found ways to survive and thrive in environments that would quickly kill most Earth organisms. These discoveries suggest that life might exist in environments throughout the solar system, and beyond that were once considered sterile. The subsurface of Mars, the clouds of Venus, the hydrocarbon lakes of Titan, and the radiation-bombarded surface of Europa all represent potential habitats where exotic forms of life might have evolved. The Drake equation, formulated by Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. The equation considers factors such as the rate of star formation, the fraction of stars with planets, the number of planets in habitable zones, and the likelihood that life develops intelligence and technology. While many of the equation's variables remain highly uncertain, it provides a framework for thinking about the prevalence of life in the cosmos. Recent estimates based on exoplanet discoveries suggest that there could be billions of potentially habitable planets in our galaxy alone. If even a tiny fraction of these worlds developed life, and an even smaller fraction developed intelligence, the galaxy could still contain thousands or millions of civilizations. Yet the continued silence of the cosmos raises profound questions about the nature and longevity of intelligent life. The concept of a post-biological universe suggests that biological intelligence might be only a brief phase in the evolution of life. Advanced civilizations might transcend their biological origins, uploading their consciousness into artificial substrates, or merging with artificial intelligence to create forms of existence we cannot imagine. Such civilizations might be unrecognizable to us and might communicate through methods that bear no resemblance to the radio signals we search for. As we continue to search the cosmos for signs of life, we are reminded that absence of evidence is not evidence of absence. The universe is vast beyond imagination, and we have barely begun to explore it. Every star system we study, every exoplanet we analyze, every radio signal we examine, brings us closer to answering the fundamental question of whether we are alone. The search for extraterrestrial life is ultimately a search for our place in the cosmos. Whether we find microbial life in the subsurface oceans of distant moons, detect technosignatures from advanced civilizations, or continue to find ourselves alone in an apparently empty universe, the answer will fundamentally change our understanding of life, intelligence, and our cosmic significance. In the meantime, we continue to listen, to watch, and to wonder about the countless worlds that orbit in the darkness beyond our reach. Standing beneath the starlit sky on a clear night, we can see with our naked eyes perhaps 3,000 individual stars, each one a distant sun that may harbor worlds of its own. These points of light appear close enough to reach out and touch, yet they represent distances so vast that they challenge the very foundations of human exploration. The journey to even the nearest star would require technological capabilities far beyond anything we currently possess, and crossing the galaxy would demand resources and timescales that dwarf human civilization itself. The dream of interstellar travel has captured human imagination for generations, inspiring countless works of science fiction and driving theoretical physicists to explore the fundamental limits of space and time. Yet as we peer deeper into the cosmos and better understand the true scale of interstellar distances, we are confronted with challenges that may prove insurmountable. Barriers imposed not by our current technology, but by the laws of physics themselves. Alpha Centauri, our nearest stellar neighbor, lies just over 4 light-years away, a distance that seems modest when expressed in cosmic terms. Yet this apparently small gap represents about 25 trillion miles, or roughly 6,000 times the distance from Earth to Pluto. To reach Alpha Centauri with our fastest current spacecraft would require over 70,000 years, a journey spanning 3,000 human generations. The Voyager probes, humanity's most distant ambassadors, provide a sobering perspective on interstellar distances. Launched in 1977, these spacecraft have traveled for over 4 decades and are now beyond the influence of our Sun, drifting through the vast emptiness of interstellar space. Yet, at their current speed, they would need over 17,000 years to reach the distance of Alpha Centauri, and they are not even heading in that direction. The fundamental challenge of interstellar travel lies not just in distance, but in the relationship between energy and velocity. According to Einstein's special theory of relativity, as an object approaches the speed of light, its mass effectively increases, requiring ever greater amounts of energy to accelerate it further. To accelerate even a small spacecraft to 10% of light speed would require energy equivalent to the total annual output of hundreds of power plants. Chemical rockets, which have carried humans to the moon, and robotic probes throughout the solar system, are fundamentally inadequate for interstellar travel. The specific impulse of chemical fuels, a measure of their efficiency, is simply too low to achieve the velocities needed for reasonable interstellar journey times. Even the most advanced chemical propulsion systems can accelerate a spacecraft to only a tiny fraction of the speed required for interstellar travel. Nuclear propulsion offers significantly better performance than chemical rockets, potentially reducing interstellar journey times from tens of thousands of years to thousands of years. Project Orion, conceived in the 1950s, proposed using nuclear explosions to propel spacecraft, while more recent concepts like nuclear thermal and nuclear electric propulsion could provide the sustained thrust needed for long-duration missions. The nuclear pulse propulsion concept envisions a spacecraft riding the shockwaves of nuclear explosions, each detonation pushing the craft to higher velocities. Theoretical studies suggest that such a system could potentially reach 5 to 10% of light speed, reducing the journey to Alpha Centauri to 40 to 80 years. However, the engineering challenges of building a spacecraft that could survive repeated nuclear explosions, combined with the political and environmental concerns about launching nuclear materials into space, make this approach extremely difficult to implement. Fusion ramjets represent another theoretical approach to interstellar propulsion. These engines would scoop up hydrogen from the interstellar medium and fuse it to provide thrust, theoretically allowing a spacecraft to accelerate continuously throughout its journey. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, could potentially reach significant fractions of light speed, but the engineering challenges are staggering. The interstellar medium, once thought to be empty space, actually contains about 1 atom per cubic centimeter, mostly hydrogen with traces of heavier elements. A fusion ramjet would need to collect this sparse material using magnetic fields stretching thousands of kilometers across, compress it to fusion densities, and extract useful energy from the reaction. The magnetic field generators alone would need to be larger than any structure humans have ever built. Recent research has revealed additional problems with the ramjet concept. At high velocities, the interstellar medium begins to act like a headwind, creating drag that could prevent the spacecraft from reaching the speeds necessary for efficient fusion. The very material the ramjet depends on for fuel could become a barrier to achieving interstellar velocities. Solar sails and their advanced cousins, laser-propelled light sails, offer a different approach to interstellar propulsion. These ultra-lightweight spacecraft use the pressure of photons, particles of light, to provide thrust. While the force is tiny, it can operate continuously without requiring fuel, potentially accelerating a spacecraft to significant fractions of light speed over time. The Breakthrough Starshot project, announced in 2016, proposes using powerful ground-based lasers to accelerate tiny spacecraft called nanocrafts to 20% of light speed. These stamp-sized probes would weigh only a few grams each and would be propelled by light sails just meters across. The laser array would need to be more powerful than any ever built, delivering gigawatts of energy in precisely focused beams. If successful, the Starshot nanocrafts could reach Alpha Centauri in just 20 years, sending back data and images from humanity's first interstellar mission. However, the technological challenges are immense. The spacecraft would need to survive the intense acceleration phase, navigate through space without guidance, and transmit data across interstellar distances using antennas smaller than a coin. The problem of communication across interstellar distances adds another layer of complexity to any interstellar mission. Radio signals from Alpha Centauri would take over 4 years to reach Earth, making real-time control impossible. Spacecraft would need to operate autonomously for decades or centuries, making decisions and conducting observations without human guidance. The data transmission challenge becomes even more severe for distant destinations. A spacecraft at Proxima Centauri would need to transmit data with enough power to be detected by Earth-based receivers across 25 trillion miles of space. The signal would be incredibly weak by the time it reached Earth, requiring sensitive receivers and sophisticated signal processing to extract useful information. Breakthrough technologies like the Alcubierre drive offer tantalizing possibilities for faster-than-light travel, though they remain purely theoretical. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, would work by contracting space in front of a spacecraft and expanding space behind it, allowing the craft to effectively travel faster than light without violating relativity. The energy requirements for an Alcubierre drive are staggering, initially calculated to require the mass energy equivalent of the entire observable universe. Later refinements reduced this to merely the mass of Jupiter, still far beyond any conceivable technology. The drive would also require exotic matter with negative energy density, something that may not exist in nature. Wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe, represent another speculative approach to interstellar travel. If traversable wormholes exist, they could potentially allow instant travel between stars separated by thousands of light years. However, general relativity suggests that such wormholes would be highly unstable and would collapse before anything could pass through them. The concept of generation ships offers a more conservative approach to interstellar colonization. These massive spacecraft would carry entire communities of humans on journeys lasting centuries or millennia, with multiple generations living and dying during the voyage. The descendants of the original crew would eventually arrive at their destination, establishing humanity's first interstellar colony. Generation ships would need to be essentially self-sufficient worlds, capable of recycling air, water, and nutrients, while maintaining complex ecosystems for centuries. The psychological and social challenges of such missions would be unprecedented, as entire civilizations would live and develop within the confines of a spacecraft. The risk of system failures, social breakdown, or genetic bottlenecks during such long journeys could doom the mission before it reaches its destination. Suspended animation or cryogenic preservation could potentially solve some of the problems of generation ships by allowing crews to sleep through most of the journey. However, current cryogenic technology cannot preserve human life for extended periods, and the energy requirements for maintaining cryogenic systems for centuries would be enormous. The search for nearby exoplanets has revealed several potentially interesting destinations for future interstellar missions. Proxima Centauri b, orbiting our nearest stellar neighbor, appears to be roughly Earth-sized and orbits within its star's habitable zone. However, Proxima Centauri is a red dwarf star known for violent flares that could sterilize any planets in its vicinity. The TRAPPIST-1 system, 39 light-years away, contains 7 Earth-sized planets and offers multiple potential destinations within a single star system. The journey would take nearly 200 years, even at 20% of light speed, but the presence of multiple worlds would provide options for exploration and potential colonization. Wolf 359, located just 7.9 light-years away, hosts at least 2 planets, including one super-Earth that might be habitable. Barnard's star, 6 light-years distant, has at least 1 confirmed planet, though it appears to be too cold for liquid water. Each of these nearby systems presents its own challenges and opportunities for future interstellar exploration. The engineering challenges of interstellar travel extend beyond propulsion to every aspect of spacecraft design. Materials must survive decades or centuries in the harsh environment of space, withstanding radiation, micrometeorite impacts, and the extreme temperatures of interstellar space. Electronic systems must operate reliably for time periods far longer than any human technology has been tested. Artificial intelligence will likely play a crucial role in any interstellar mission, as the communication delays make human control impossible. The AI systems would need to be sophisticated enough to handle unexpected situations, make complex decisions, and even repair or modify the spacecraft as needed. The reliability requirements for such systems far exceed anything in current technology. The motivation for interstellar travel goes beyond scientific curiosity to touch on fundamental questions about humanity's future. As we face challenges on Earth ranging from climate change to resource depletion, some argue that expanding beyond our solar system represents humanity's best hope for long-term survival. Establishing self-sustaining colonies around other stars would ensure that human civilization could survive even catastrophic events that might destroy life on Earth. However, the resources required for interstellar travel could alternatively be used to address problems here on Earth, or to establish colonies within our solar system. Mars, the moons of Jupiter and Saturn, and even asteroids could potentially support human communities using technology far less advanced than that required for interstellar travel. The timescales involved in interstellar exploration challenge our understanding of human civilization itself. A journey to even the nearest stars would span many human generations, raising questions about the continuity of purpose and technology across centuries. The civilizations that launch interstellar missions might be very different from those that eventually receive the results. As we contemplate the vast distances between stars and the technological challenges they present, we are reminded that the universe sets fundamental limits on exploration and expansion. The speed of light represents an absolute barrier that cannot be exceeded, and the energy requirements for interstellar travel grow exponentially as we approach this limit. Yet human ingenuity has repeatedly overcome seemingly impossible challenges, from flight to space travel to landing on the moon. The dream of reaching the stars continues to inspire new generations of scientists and engineers, driving the development of technologies that could eventually make interstellar travel possible. Perhaps most importantly, the study of interstellar travel pushes us to think on cosmic timescales and to consider humanity's place in the broader universe. Even if we never reach the stars ourselves, the attempt teaches us about the limits of technology, the nature of space and time, and our own cosmic significance. In the meantime, we continue to explore our local neighborhood, sending robotic probes to the outer planets and preparing for human missions to Mars. Each step outward from Earth teaches us lessons that could eventually be applied to the far greater challenge of interstellar exploration. The journey to the stars may take centuries or millennia to accomplish, but it begins with the first steps we take beyond our home world. When we step back from the familiar scale of planets and stars, even beyond the vast collections of stars we call galaxies, we discover that the universe organizes itself into structures so immense that they challenge our ability to comprehend scale itself. These are the largest known structures in the cosmos, formations that span hundreds of millions or even billions of light years, creating a cosmic architecture that reveals the fundamental nature of space, time, and matter on the grandest scales imaginable. The story of cosmic structure begins with the cosmic web, a vast network of dark matter filaments that stretches across the observable universe like the threads of an inconceivably large spider's web. This web represents the scaffolding upon which all visible matter in the universe is arranged, with galaxies strung along its filaments like dewdrops on gossamer strands, while vast empty spaces, called cosmic voids, separate the threads of this celestial tapestry. To understand the cosmic web, we must first envision the universe not as a collection of isolated galaxies scattered randomly through space, but as a connected network where matter flows along preferred pathways, carved out by gravity over billions of years. These pathways, invisible to our telescopes but detectable through their gravitational effects, form the largest coherent structures known to exist. The cosmic web emerged from tiny fluctuations in the density of matter in the early universe, variations so small they amounted to differences of only 1 part in 100,000. Yet over cosmic time, gravity amplified these minute differences, causing regions of slightly higher density to attract more matter, while regions of lower density became increasingly empty. This process, called gravitational collapse, created the hierarchical structure we observe today. Computer simulations of cosmic evolution show how these initial fluctuations grew into the cosmic web we observe. In the early universe, dark matter formed vast halos that later became the sites of galaxy formation. These halos were not isolated, but connected by streams and filaments of dark matter, creating a network that guided the flow of ordinary matter throughout the cosmos. The filaments of the cosmic web span distances of 100 to 200 million light-years, making them among the largest coherent structures in the universe. They contain most of the ordinary matter in the cosmos, though much of it remains invisible to our telescopes, existing as hot gas in the spaces between galaxies. This intergalactic medium is so tenuous that it produces only the faintest glow, yet it connects the visible galaxies like roads connecting distant cities. Where multiple filaments intersect, we find the nodes of the cosmic web, massive concentrations of matter that host galaxy clusters and superclusters. These are the most massive gravitationally bound structures in the universe, containing hundreds or thousands of galaxies held together by enormous halos of dark matter. The largest galaxy clusters contain the mass of millions of billions of suns, spread across regions tens of millions of light-years across. The Virgo supercluster, which contains our own local group of galaxies, represents one of these cosmic web nodes. Spanning about 110 million light-years, it contains over 1,000 galaxies, including the massive Virgo cluster at its center. Yet even this enormous structure is itself part of a larger formation called the Laniakea supercluster, which stretches across 520 million light-years and contains the mass of 100 quadrillion suns. The discovery of Laniakea in 2014 revolutionized our understanding of cosmic structure and our place within it. Using measurements of galaxy velocities, astronomers mapped the flow of matter in our local region of the universe, revealing that hundreds of thousands of galaxies, including our own Milky Way, are all flowing toward a massive concentration of matter called the Great Attractor. The Great Attractor, located roughly 150 million light-years away in the direction of the constellation Centaurus, represents one of the most mysterious structures in our cosmic neighborhood. Hidden behind the dense star fields of our own galaxy, this enormous concentration of matter exerts a gravitational pull so strong that it influences the motion of galaxies across hundreds of millions of light-years. Yet much of its mass remains invisible, composed of dark matter and dim galaxies that we are only beginning to detect. Beyond the Great Attractor lies an even more massive structure called the Shapley supercluster, located about 650 million light-years away. This enormous concentration of galaxies may be the largest gravitationally bound structure in our observable universe, containing dozens of galaxy clusters and the mass of tens of thousands of Milky Way galaxies. The gravitational influence of the Shapley supercluster can be detected in the motion of galaxies across billions of light-years. The cosmic web reveals itself most clearly in large galaxy surveys that map the three-dimensional distribution of galaxies across vast volumes of space. Projects like the Sloan Digital Sky Survey and the upcoming Vera Rubin Observatory have mapped millions of galaxies, revealing the web-like structure of the universe in exquisite detail. These surveys show that galaxies are not randomly distributed, but follow the filamentary structure predicted by theories of cosmic evolution. Between the filaments and nodes of the cosmic web lie cosmic voids, vast regions of space that contain very few galaxies. These voids are not completely empty, but they are so sparse that a galaxy placed in the center of a large void would see almost no other galaxies in any direction. The largest known void, the Boötes void, or Great Nothing, spans about 330 million light-years and contains almost no visible matter, Cosmic voids make up about 80% of the universe's volume, yet they contain only a small fraction of its matter. Within these voids, space itself expands faster than average due to the influence of dark energy, the mysterious force that drives the acceleration of cosmic expansion. The voids grow larger over time, creating ever vaster empty regions between the filaments of matter. The study of cosmic voids provides unique insights into the nature of dark energy and the expansion of the universe. Because voids contain very little matter, they are dominated by dark energy, making them natural laboratories for studying this mysterious force. Observations of void properties and evolution help astronomers understand how dark energy has influenced the growth of cosmic structure over billions of years. The boundaries between voids and filaments are marked by vast walls of galaxies, sheet-like structures that can extend for hundreds of millions of light years. The most famous of these structures is the Great Wall, also known as the CFA homunculus, which stretches for about 500 million light years and was one of the first large-scale structures discovered in galaxy surveys. Even larger structures have since been discovered, including the Sloan Great Wall, which extends for over 1 billion light years, making it one of the largest known structures in the observable universe. These walls represent the largest coherent arrangements of matter known to exist, yet they are also among the most fragile, being only a few galaxies thick in most places. The Hercules Corona Borealis Great Wall, discovered in 2013, may be the largest structure ever detected, potentially spanning up to 10 billion light years. This structure consists of gamma-ray bursts that appear to be aligned in a vast wall-like formation, though its exact nature and extent remain subjects of ongoing research. If confirmed, it would represent a structure so large that it challenges our understanding of cosmic homogeneity. The cosmic web is not static, but evolves over cosmic time, with filaments growing stronger and voids becoming larger and emptier. Computer simulations show that the web will continue to evolve for billions of years into the future, with galaxy clusters merging to form ever larger structures, while the accelerating expansion of space driven by dark energy eventually separates the filaments. In the far future, dark energy will dominate cosmic evolution, causing the expansion of space to accelerate until even gravitationally bound structures begin to separate. The cosmic web will gradually dissolve as galaxies within clusters are pulled apart by the expansion of space, leaving behind isolated galaxies drifting through an ever-expanding and increasingly empty universe. The discovery of the cosmic web has revealed that the universe possesses structure on scales approaching the size of the observable universe itself. The largest structures we can observe span roughly 1/3 of the distance to the cosmic horizon, suggesting that we are seeing the universe's architecture on its fundamental scales. These observations support the idea that the universe is homogeneous on the largest scales, with no structures larger than a few billion light years. Recent observations have begun to detect the cosmic web directly by observing the faint emission from hydrogen gas that lies along the dark matter filaments. This intergalactic medium glows with the faint light of hydrogen atoms excited by ultraviolet radiation from stars and quasars, creating a cosmic web of light that traces the underlying dark matter structure. These observations provide the first direct view of the cosmic web itself, rather than just the galaxies that mark its location. The Lie Alpha forest, observed in the spectra of distant quasars, provides another window into the cosmic web. As light from quasars travels through space, it encounters clouds of hydrogen gas along dark matter filaments, creating absorption lines that reveal the distribution of matter along the line of sight. This technique allows astronomers to map the cosmic web in 3 dimensions, revealing its structure across billions of years of cosmic history. Galaxy clusters, the most massive nodes of the cosmic web, are themselves connected by bridges of dark matter and hot gas. Recent observations with X-ray telescopes have detected these bridges directly, showing streams of hot gas flowing between galaxy clusters along cosmic web filaments. These observations confirm that galaxy clusters are not isolated islands, but are connected by the vast network of the cosmic web. The study of cosmic structure has revealed that we live in a universe that is both highly structured and mostly empty. The matter we can see, the stars and galaxies that light up the night sky, represents only the tip of an iceberg, marking the locations of vast but invisible structures made primarily of dark matter. These structures span scales so large that they encompass the entire observable universe, yet they emerged from fluctuations so small that they were barely detectable in the early cosmos. The cosmic web also provides insights into the fundamental nature of space and time. The largest structures in the universe are so large that light has not had time to travel across them since the beginning of the universe. This means that different parts of these structures have never been in causal contact, yet they exhibit coherent organization that reflects the initial conditions of the Big Bang. As we map the cosmic web in ever greater detail, we are creating a census of the universe's largest structures and beginning to understand how they formed and evolved. Each new survey reveals structures that push the boundaries of what we thought possible, challenging our understanding of cosmic evolution and the fundamental laws of physics that govern the universe on its largest scales. The cosmic web represents the universe's architecture, a vast framework that organizes matter and energy across scales larger than anything we experience in our daily lives. It is a structure so large that it encompasses everything we can observe. Yet it is also a structure that we are only beginning to understand. As we continue to map and study the cosmic web, we are literally charting the skeleton of the universe itself, revealing the framework upon which all cosmic evolution has unfolded. As we stand at the threshold of a new era in space exploration, looking out into the cosmic darkness that has beckoned humanity for millennia, we find ourselves equipped with technologies that would have seemed like magic to previous generations. Yet, for all our achievements, for all the robotic ambassadors we have sent to distant worlds, and all the telescopes that peer deep into space and time, we remain at the very beginning of our journey into the infinite expanse that surrounds us. The future of space exploration stretches before us like an uncharted ocean, filled with possibilities that challenge our imagination and engineering capabilities in equal measure. In the coming decades, we will witness the emergence of technologies and missions that will fundamentally transform our understanding of the universe and our place within it, opening doors to realms that have existed only in our dreams and scientific speculation. The James Webb Space Telescope, humanity's most powerful window into the cosmos, has already begun to revolutionize our understanding of the early universe, exoplanet atmospheres, and stellar formation. This remarkable instrument can peer deeper into space and time than any telescope before it, observing galaxies as they appeared when the universe was young, and analyzing the atmospheric composition of worlds orbiting distant stars. Future space telescopes will dwarf even the James Webb in their capabilities and ambition. The proposed Habitable Exoplanet Observatory, a next-generation space telescope designed specifically to search for signs of life on distant worlds, could directly image Earth like planets orbiting nearby stars and analyze their atmospheres for biosignatures. Such a telescope would require unprecedented precision and stability, maintaining alignment to billionths of a degree while operating millions of kilometers from Earth. The concept of telescope interferometry, where multiple telescopes work together as a single enormous instrument, promises to provide resolution equivalent to telescopes the size of Earth or even larger. The Event Horizon Telescope has already demonstrated this technique by creating the first images of black hole event horizons, but future interferometer arrays could extend into space, creating virtual telescopes with baselines stretching across the solar system. A space-based interferometer with telescopes separated by the distance from Earth to Jupiter could theoretically resolve features on the surface of exoplanets, potentially detecting continents, oceans, and even large cities if they exist. Such observations would represent the ultimate expression of remote sensing, allowing us to study alien worlds in detail without ever leaving our solar system. The search for life beyond Earth is entering a new phase as we prepare to explore the subsurface oceans of Europa, Enceladus, and other potentially habitable moons. The Europa Clipper mission, scheduled to launch in the 2020s, will conduct detailed reconnaissance of Jupiter's ice-covered moon, mapping its subsurface ocean and searching for locations where the ocean might be accessible from the surface. Future missions to Europa could include ice-penetrating probes that would melt through the moon's frozen crust to directly sample the ocean beneath. These cryobots would need to be completely sterile to avoid contaminating Europa's environment, while also being sophisticated enough to search for signs of life in an alien ocean that has been isolated from the surface for billions of years. The Dragonfly mission to Titan represents a new paradigm in planetary exploration, using a nuclear-powered helicopter to explore the surface of Saturn's largest moon. This rotorcraft will be able to fly between different locations on Titan's surface, studying the moon's complex organic chemistry and searching for signs of past or present life. Dragonfly's success could pave the way for flying missions to other worlds with atmospheres, including Venus, Mars, and the ice giants. Mars exploration is entering its most ambitious phase yet, with multiple space agencies planning sample return missions, human expeditions, and eventually permanent settlements. The Perseverance rover has already collected samples of Martian rock and soil that will be returned to Earth by future missions, providing scientists with pristine Martian material to study in terrestrial laboratories. Human missions to Mars represent one of the greatest challenges in space exploration, requiring life support systems that can operate reliably for years, radiation shielding to protect astronauts during the long journey, and in situ resource utilization systems that can produce fuel, water, and oxygen from the Martian environment. The first human missions to Mars will likely establish temporary research outposts, but they will lay the groundwork for permanent human settlements on another world. The establishment of a permanent human presence on Mars would mark a turning point in human civilization, creating the first self-sustaining human community beyond Earth. Such a settlement would need to be largely self-sufficient, producing its own food, manufacturing its own equipment, and maintaining complex life support systems with minimal support from Earth. The psychological and social challenges of Martian colonization may prove as difficult as the technical ones. Asteroid mining represents another frontier that could transform space exploration by providing the resources needed for large-scale construction projects in space. A single metallic asteroid could contain more platinum than has ever been mined on Earth, while water-rich asteroids could provide the fuel needed for deep space missions. The development of asteroid mining technology could make space exploration economically self-sustaining for the first time. The construction of large space habitats, rotating structures that could house thousands or millions of people, remains a long-term goal that could enable permanent human expansion beyond Earth. These orbital cities would provide Earth-like gravity through rotation and could be powered by solar energy or nuclear reactors. The largest proposed habitats could house entire civilizations, creating backup copies of human culture and knowledge that would survive even if Earth were destroyed. Advanced propulsion technologies currently under development could dramatically reduce travel times within the solar system and make interstellar exploration feasible. Nuclear thermal and nuclear electric propulsion systems could cut journey times to the outer planets from years to months, while breakthrough concepts have to adapt their behavior based on new discoveries. Pursuing the most scientifically interesting targets, without waiting for instructions from Earth. The miniaturization of spacecraft components is enabling new classes of missions that would have been impossible with traditional technology. CubeSats, small satellites the size of bread loaves, have already demonstrated that useful science can be accomplished with tiny spacecraft. Future swarms of microspacecraft could explore multiple locations simultaneously, providing distributed observations across vast regions of space. Breakthrough Starshot and similar projects are developing the technology needed for interstellar exploration, using ultra-lightweight spacecraft propelled by powerful lasers. These gram-scale probes could reach the nearest stars within decades, transmitting data back to Earth using tiny lasers or radio transmitters. While the data capacity would be limited, such missions could provide humanity's first close-up look at exoplanets and alien star systems. The development of self-replicating spacecraft, often called von Neumann probes, could enable exponential expansion of human presence throughout the galaxy. These hypothetical machines would travel to distant star systems, use local materials to build copies of themselves, and then send those copies to even more distant destinations. While the technology for such systems remains far in the future, the concept represents the ultimate expression of space exploration. Quantum technologies could revolutionize space exploration by enabling new forms of communication, navigation, and sensing. Quantum entanglement could theoretically allow instantaneous communication across any distance, though practical quantum communication systems face significant technical challenges. Quantum sensors could detect gravitational waves, dark matter, and other phenomena with unprecedented sensitivity. The search for extraterrestrial intelligence is entering a new phase with the development of more sophisticated detection methods and the expansion of search strategies beyond radio signals. Optical SETI searches for laser pulses, while others look for the waste heat from advanced civilizations or the signatures of mega engineering projects. The discovery of even microbial life elsewhere in the universe would have profound implications for our understanding of biology and our place in the cosmos. Space-based solar power systems could provide clean energy for Earth while also powering large-scale space operations. These systems would collect solar energy in space, where it is available continuously, without atmospheric interference, and beam it to Earth using microwaves or laser light. The development of space-based solar power could make space exploration economically viable by creating valuable products that can be sold on Earth. The eventual development of space elevators or other revolutionary transportation systems could dramatically reduce the cost of reaching space, making routine travel to orbit as common as international flights are today. Carbon nanotubes, graphene, and other advanced materials could make such systems possible, though significant engineering challenges remain. As we look toward the far future, the possibility of transforming entire worlds through terraforming represents perhaps the ultimate expression of space exploration. Converting Mars into an Earth-like world would require atmospheric engineering on a planetary scale, potentially involving the release of greenhouse gases to thicken the atmosphere and raise temperatures. Such projects would take centuries or millennia to complete, but could create new homes for human civilization. The exploration of other star systems remains a distant goal, but one that continues to drive technological development and scientific research. Even if we never achieve faster than light travel, the development of generation ships or other long-duration spacecraft could enable human expansion to nearby star systems over timeframes of centuries or millennia. Perhaps most importantly, space exploration will continue to transform our understanding of fundamental physics, biology, and our place in the universe. Each new discovery opens unexpected avenues for research and exploration, revealing phenomena we never imagined and challenging our most basic assumptions about reality. The future of space exploration is not just about the destinations we will reach or the technologies we will develop. but about the transformation of human consciousness that comes from seeing ourselves as citizens of the universe rather than inhabitants of a single world. As we venture forth into the cosmic ocean, we carry with us the hopes and dreams of all humanity, seeking answers to the deepest questions about existence itself. In the decades and centuries ahead, we will witness achievements that surpass our wildest imagination, discoveries that revolutionize our understanding of the universe, and perhaps most remarkably, the gradual transformation of humanity from a single world species to a truly cosmic civilization. The journey has only just begun, and the greatest adventures lie ahead in the infinite darkness of space. As we stand on the threshold of unprecedented expansion into the cosmos, equipped with technologies that could carry human presence to other worlds, and perhaps even other star systems, we find ourselves confronting questions that extend far beyond the realm of engineering and science. The power to explore space is also the power to alter it, to contaminate pristine environments, and potentially to encounter forms of life that have evolved in complete isolation for billions of years. With this power comes a profound responsibility to consider not just what we can do, but what we should do. The ethics of space exploration touch upon some of humanity's deepest philosophical questions about our relationship with nature, our responsibilities to future generations, and our role as conscious beings in a vast and largely unconscious universe. Every mission we launch, every world we visit, every signal we send into the cosmos carries with it the weight of moral choices that could have consequences extending far beyond our current understanding. The concept of planetary protection has emerged as one of the most immediate ethical concerns in space exploration. When we send spacecraft to other worlds, we risk carrying Earth microorganisms that could contaminate alien environments, potentially destroying indigenous life forms before we even discover them. The challenge of sterilizing spacecraft completely while maintaining their functionality represents not just a technical problem, but a moral imperative to preserve the integrity of other worlds. Mars presents a particularly complex case for planetary protection ethics. As we prepare to send increasingly sophisticated missions to the Red Planet, including eventual human explorers, we must grapple with the reality that complete sterilization may be impossible. Human beings carry trillions of microorganisms in and on their bodies, and some of these hardy travelers might be able to survive in the Martian environment. The question becomes whether the scientific and social benefits of human Mars exploration justify the risk of irreversibly altering the planet's biological landscape. The subsurface oceans of Europa, Enceladus, and other icy moons present even more challenging ethical dilemmas. These hidden seas may represent some of the most promising locations for extraterrestrial life in our solar system, yet they are also extraordinarily difficult to explore without contamination. Any probe that penetrates through kilometers of ice to reach these oceans would inevitably introduce foreign material into environments that have been isolated for billions of years. The discovery of life beyond Earth would raise profound questions about our responsibilities toward alien organisms. If we encounter microbial life in the subsurface ocean of Europa, do we have the right to study it, collect samples, or establish research stations that might disrupt its environment? The frameworks we use to protect endangered species on Earth may prove inadequate for addressing the ethical challenges of interacting with life forms that evolved under completely different conditions. The possibility of encountering intelligent extraterrestrial life, however remote, forces us to consider questions that have no precedent in human experience. What protocols should govern our response to signals from alien civilizations? Who has the authority to speak for humanity in establishing contact with beings whose motivations, capabilities, and ethical frameworks we cannot comprehend? The decisions we make about how to search for and potentially contact extraterrestrial intelligence could have consequences that extend far beyond our planet. The search for extraterrestrial intelligence raises its own ethical questions about whether we should actively transmit signals into space or merely listen for communications from other civilizations. Some argue that sending powerful radio messages toward nearby star systems represents an unacceptable risk, potentially revealing our location to civilizations whose intentions we cannot know. Others contend that the benefits of establishing contact with advanced alien civilizations far outweigh the speculative risks. The concept of cosmic citizenship suggests that as we venture into space, we must consider ourselves not just as representatives of humanity, but as participants in a larger cosmic community that may include forms of life and intelligence we have not yet encountered. This perspective challenges us to think beyond immediate human interests and consider our actions in the context of universal principles that could apply to any conscious beings in the universe. Terraforming, the hypothetical process of transforming alien worlds into Earth-like environments suitable for human habitation, represents perhaps the most ethically complex undertaking humans might attempt. Converting the atmosphere and climate of Mars to support terrestrial life would amount to the largest engineering project in human history, fundamentally altering an entire world to suit our needs. Such an endeavor raises questions about whether we have the right to remake other worlds in our image, particularly if those worlds might harbor their own forms of life. The timeline for terraforming would span centuries or millennia, meaning that decisions made today would bind future generations to projects they had no role in initiating. The ethics of intergenerational responsibility become particularly acute when considering projects that would irreversibly alter entire planets. Do we have the right to commit our descendants to maintaining vast planetary engineering systems, or to foreclose their options by fundamentally changing the nature of other worlds? Environmental ethics in space exploration must also consider the sustainability of our activities within our own solar system. The growing problem of space debris around Earth demonstrates how quickly human activities can create environmental hazards that affect future exploration. As we establish permanent settlements on other worlds and begin large-scale resource extraction operations, we must develop frameworks for ensuring that space development proceeds in ways that preserve opportunities for future generations. The militarization of space presents another set of ethical challenges as nations develop capabilities for space warfare and the deployment of weapons in orbit. The peaceful exploration of space could be undermined by conflicts that extend terrestrial disputes into the cosmic realm. International treaties like the Outer Space Treaty attempt to preserve space as a realm for peaceful purposes, but the enforcement and interpretation of such agreements become increasingly complex as space capabilities advance. Resource extraction from asteroids, moons, and other celestial bodies raises questions about ownership and distribution of space-based wealth. Who has the right to claim ownership of asteroid resources worth potentially trillions of dollars? How should the benefits of space mining be distributed among the nations and individuals who invest in these technologies versus the broader human community that could benefit from the resources? The answers to these questions will shape whether space development increases or decreases inequality among human populations. The preservation of cosmic heritage sites represents an emerging field in space ethics as we consider how to protect locations of scientific, historical, or cultural significance from the impacts of increasing space activity. The Apollo landing sites on the Moon, for example, represent irreplaceable artifacts of human achievement that could be damaged by future lunar development. Similarly, sites of particular scientific interest, such as the polar ice caps on Mars or the geysers of Enceladus, may warrant special protection from industrial or tourist activities. The long-term survival of human civilization may depend on establishing self-sustaining settlements beyond Earth. Yet such settlements would face ethical challenges, unlike any in human history. How do we ensure that space settlements develop democratic governance structures and protect individual rights when they are completely dependent on complex technological systems for survival? What obligations do Earth-based societies have to support space settlements during emergencies? And what rights do space settlers have to independence from terrestrial authority? The psychological and social impacts of space exploration on both explorers and Earth-based populations raise additional ethical considerations. Long-duration space missions expose astronauts to isolation, radiation, and other hazards that could have lasting effects on their physical and mental health. The informed consent process for such missions must grapple with risks that are not fully understood and may not manifest until years or decades after exposure. The cultural impacts of space exploration extend beyond the immediate participants to affect how all of humanity understands its place in the universe. The images of Earth from space have already transformed human consciousness, creating a perspective that transcends national and cultural boundaries. As we discover life elsewhere or establish permanent settlements on other worlds, these developments will continue to reshape human identity and values in ways we cannot fully predict. The distribution of benefits and risks from space exploration raises questions of global justice, as the most advanced spacefaring nations reap the immediate benefits of space technology, while the costs and risks are shared more broadly. Climate change, asteroid impacts, and other planetary scale threats affect all of humanity. Yet the capabilities to address these challenges through space technology remain concentrated in a few wealthy nations. Educational and cultural access to space exploration represents another dimension of space ethics, as we consider how to ensure that the inspiration and knowledge gained from exploring the cosmos is shared broadly rather than restricted to elite populations. The democratization of space exploration through CubeSats, citizen science projects, and public outreach programs helps ensure that space exploration serves the broader human community rather than narrow interests. The precautionary principle suggests that when facing potentially irreversible consequences with incomplete knowledge, we should err on the side of caution. In space exploration, this principle might argue for more extensive planetary protection measures, more careful consideration of contact protocols, and more conservative approaches to terraforming and resource extraction. However, excessive caution could also prevent beneficial developments that could enhance human welfare and scientific knowledge. The philosophical implications of discovering life elsewhere in the universe would challenge many of our most fundamental assumptions about the nature and purpose of existence. If life proves to be common throughout the cosmos, it would suggest that consciousness and intelligence may be fundamental features of the universe rather than rare accidents. Such discoveries could transform our understanding of biology, consciousness, and our cosmic role. Future generations will inherit the consequences of the decisions we make today about space exploration and development. The ethical frameworks we establish now will influence whether space becomes a realm of peaceful cooperation and scientific discovery, or an extension of terrestrial conflicts and exploitation. The choices we make about planetary protection, resource allocation, and contact protocols will shape the cosmic legacy we leave for our descendants. As we venture forth into the infinite darkness of space, we carry with us not just the hopes and dreams of humanity, but also the responsibility to act as ethical ambassadors of our species and our planet. The universe may be vast and largely unconscious, but within it exists at least one world where conscious beings have developed the capacity for moral reasoning and ethical choice. How we exercise that capacity as we explore the cosmos may be among the most important decisions our species ever makes. The exploration of space is ultimately an exploration of ourselves, revealing not just what lies beyond our world, but what kind of beings we choose to become as we take our first steps into the cosmic ocean. In the end, the greatest discovery we might make is not what exists in the darkness between the stars, but what it truly means to be human in a universe full of infinite possibilities. As our journey through the unexplored realms of space draws to a close, we find ourselves returned to where we began, beneath the same star-filled sky that has inspired wonder and curiosity in countless generations before us. Yet now, having traveled through the cosmic scales from our own solar system to the largest structures in the universe, from the search for life to the ethics of exploration, we see these familiar stars with new eyes, understanding both how much we have learned and how much mystery still awaits our discovery. The darkness above us is no longer simply empty space punctuated by distant lights, but a vast ocean of possibility stretching beyond the limits of imagination. Each point of light represents not just a star, but potentially an entire system of worlds, some perhaps harboring life, others offering resources or knowledge that could transform human civilization. The spaces between the stars, once thought to be empty voids, now reveal themselves as part of an intricate cosmic web, threaded with dark matter filaments and filled with the faint whispers of ancient light. We have learned that our solar system, once the extent of human knowledge about planetary worlds, represents only the smallest sample of cosmic diversity. Beyond the familiar planets of our childhood, astronomy books lie realms of ice and fire, worlds with diamond rain and methane seas, moons with hidden oceans that may teem with alien life. Each discovery reveals new possibilities for the emergence and evolution of life, expanding our understanding of what it means to be alive in this vast universe. The search for life beyond Earth has taught us that the universe may be far stranger and more wonderful than we ever imagined. From the extremophiles thriving in Earth's most hostile environments to the potential alien biospheres hidden beneath the icy crusts of distant moons, we are learning that life is remarkably adaptable and persistent. Whether we are alone or part of a cosmic community of living worlds remains one of the greatest mysteries awaiting our exploration. The dark universe that surrounds the islands of light we call galaxies has revealed itself to be the dominant component of reality, composed of mysterious substances that we can detect but not yet understand. Dark matter and dark energy, which together make up 95% of the universe, remind us that our knowledge is still in its infancy. We are like children playing on the beach of an infinite ocean, occasionally finding a beautiful shell or smooth stone while the vast depths remain unexplored. Our contemplation of interstellar travel has shown us both the incredible distances that separate us from other star systems and the ingenuity of human creativity in imagining solutions to seemingly impossible challenges. Whether through breakthrough physics that could enable faster than light travel, or through the patient construction of generation ships that carry human civilization across the cosmic void, the dream of reaching other stars continues to inspire and challenge us. The largest structures in the universe, those vast webs of matter and energy that span billions of light years, have revealed the universe to be organized on scales that dwarf even our expanded sense of cosmic distance. These structures emerge from the smallest fluctuations in the early universe, demonstrating how the tiniest variations can grow over cosmic time into formations larger than anything we can directly comprehend. Looking toward the future, we see a time when the boundaries between the possible and impossible may be redrawn by technologies we are only beginning to imagine. Space telescopes of unprecedented power will peer into the atmospheres of distant worlds, searching for the chemical signatures of life. Robotic explorers will dive beneath the ice of alien moons, tasting waters that have been hidden from starlight for billions of years. Human beings may walk on the red plains of Mars, establishing the first permanent human settlements beyond Earth. Yet perhaps the most profound impact of space exploration lies not in the destinations we reach or the technologies we develop, but in the transformation of human consciousness that comes from seeing ourselves as part of something infinitely larger. The perspective from space has already begun to dissolve the artificial boundaries that divide us, revealing Earth as a single integrated system where all life shares a common origin and destiny. The ethical questions we have explored remind us that with the power to explore the cosmos comes the responsibility to do so wisely. As we venture into space, we carry with us the accumulated wisdom and folly of human civilization, the capacity for both creation and destruction that has shaped our history on Earth. The choices we make about how to explore space, how to treat the environments we encounter, and how to share the benefits of cosmic knowledge will determine whether space exploration becomes a force for unity and enlightenment, or an extension of terrestrial conflicts into the cosmic realm. The silence of the cosmos, the absence of obvious signs of extraterrestrial intelligence despite the vast number of potentially habitable worlds, presents us with one of the most puzzling aspects of our cosmic situation. Whether this silence indicates that intelligence is exceedingly rare, that civilizations tend to destroy themselves before achieving interstellar communication, or simply that we do not yet know how to recognize the signs of alien intelligence, remains one of the great mysteries of our time. As we rest beneath the stars tonight, we can take comfort in knowing that we live at a remarkable moment in cosmic history. We are among the first generations of humans to understand our place in the universe, to see galaxies billions of light years away, to detect planets orbiting other stars, and to seriously contemplate the possibility of life arising independently elsewhere in the cosmos. We stand at the threshold of discoveries that could answer some of humanity's oldest questions about our cosmic origins and destiny. The universe stretches out before us, vast beyond comprehension, yet filled with patterns and structures that reveal themselves to patient observation and careful thought. From the quantum fluctuations in the vacuum of space to the largest superclusters of galaxies, from the chemical processes that enable life to the dark energy that drives cosmic expansion, the universe operates according to principles we are only beginning to understand. In the centuries and millennia ahead, human beings or their descendants may spread throughout the solar system and eventually to other star systems, carrying with them the light of consciousness to illuminate corners of the universe that have remained dark since the beginning of time. Whether this expansion takes the form of biological humans, artificial intelligences, or something we cannot yet imagine, the essence of human curiosity and wonder will continue to drive exploration and discovery. The night sky above us is both our past and our future, containing the light of stars that died before Earth was born, and the destinations toward which our species may one day journey. In its depths lie answers to questions we have not yet learned to ask, and mysteries that will challenge our understanding for generations to come. As you close your eyes beneath the cosmic dome, let your mind wander among the stars, across the light years that separate us from distant worlds, through the cosmic web that connects all matter in the universe, and into the infinite possibilities that await discovery. The universe is patient, eternal, and filled with wonders beyond imagination. It has waited 13.8 billion years for conscious beings to arise and contemplate its mysteries, and it will continue to reveal its secrets to those who seek to understand. In the silence of the cosmic night, in the gentle glow of starlight that has traveled for years or centuries to reach your eyes, in the vast spaces between galaxies where dark matter flows in invisible currents, the universe continues its ancient dance of creation and destruction, expansion and evolution. And we, small as we are in the cosmic scheme, are privileged to be conscious participants in this grand cosmic story. Sleep well beneath the infinite stars, knowing that the greatest adventures in exploration and discovery lie ahead, waiting for future generations to unlock the secrets of the cosmos, and perhaps, one day, to find that we are not alone in the vast darkness of space. The journey into the unknown has only just begun, and the horizon of possibility stretches endlessly before us into the infinite night.